Good afternoon to all of you. It is with great pleasure that I extend my heartfelt welcome to you all to the University Distinguished Lecture Series 16. I am delighted and honored to welcome our distinguished speaker, Professor Umesh V Waghmare, our highly respected advisor, Professor V.S. Rao, our beloved Registrar Sir, Dr. R. Prem Kumar, our Dean of Research, Professor Ranjit Thapa, to the stage. I also would like to welcome all our deans, directors, sir, our research scholars, students to this University Distinguished Lecture Series. Now, I would like to request our advisor, sir, Professor V.S. Rao, to give a welcome address.
Good afternoon, everybody. Respected Professor Umesh V Waghmare, sir, today's University's distinguished lecture speaker, Registrar Dr. Prem Kumar, Dean Research Professor Ranjit Thapa, Vice Chancellor Manoj sir, who could not join us because of slight indisposition, deans, faculty, my dear students, and all other participants from all over the country and other places. At the very outset, I extend a warm welcome to Professor Waghmare and profusely thank him for having accepted to deliver the 16th University Distinguished Lecture today on a topic of great importance. For the information of those, we have started this around 2 years ago with the initiative of some of our young enthusiastic faculty. The first University Distinguished Lecture Series was delivered as an inaugural lecture delivered by Professor Ajay K. Sood, who is presently Principal Scientific Advisor to the Prime Minister. I also welcome all the participants from our university and outside for having taken time to attend this lecture. SRM University has many best practices. Of course, this is one such type of practice. We are extremely grateful to you, sir, and to all the 15 distinguished speakers who have delivered excellent lectures on topics of great importance, which has inspired and motivated many faculty and students to pursue their studies as well as research. For the benefit of the participants from outside who are not so well aware of about our university, I would like to state some facts that this university was established in the year 2016 by SRM Trust under the AP Private University Act. Started with a modest beginning with 250 students in 3 programs. If I correctly recall, it must be computer science engineering, electronics and communications engineering, and mechanical engineering, with 32 faculty. Not much of infrastructure. What you see, the beautiful infrastructure was not existing at that time. Today, we have around 7,000 students, out of which 160 are international students, and we have around 300 faculty. Especially, our faculty are 100% PhD, with almost all of them having international exposure. That is the reason why, in the very beginning itself, in the first 2-3 years itself, we could make a dent and create a record with their scientific accomplishments. Today, our faculty have published good number of publications, around 1634 publications in Scopus indexed journals with 8,000 odd citations. They have published around 150 patents. We have around 75 research projects to the tune of 32 crores. All this has become possible because of the recruitment of the excellent faculty right from the beginning. We now conduct degree programs at all the 3 tiers of higher education in around 20 different disciplines, because our vision was to become a multidisciplinary research intensive university, a world-class university, globally recognized, nationally relevant, and regionally transformative university. So with good faculty, and quality students, we have never compromised on the quality of students. We could make the progress. We have achieved many laurels. Our faculty have got number of publications in Nature Index journals. Some of our faculty are in the top 2% of researchers, the data prepared by Stanford Research. Like this, there are many. Our students also have many accomplishments. Especially we have a semester abroad program at UC Berkeley and UC Davis and some more universities like NUS Singapore, etc. Our international relations and higher studies have done a very good work by placing our students in several well-reputed QS-ranked universities all over the world. With this accomplishment, the university is marching forward under the stewardship of our President, Dr. Satyanarayanan, and our Vice Chancellor, Professor Manoj Arora, and our excellent faculty. I'm sure this university will reach its peaks very soon. I wish all the best for the university and all the best for the graduating students, because the placements are also 100% placements during all the previous years with excellent salary packages, around 10 lakhs average. And we lay a lot of emphasis on entrepreneurship. We want 20% of our students to be entrepreneurs. Accordingly, an ecosystem has been created. Several companies are graduating. Several measures have been taken to promote entrepreneurship in this university. So let me come back to the lecture today. Once again, I am extremely thankful to you, sir, for going to deliver this 16th University Distinguished Lecture. An eminent personality. Presently, he is a president of Indian Science Congress, and also he is at Jawaharlal Nehru Center of Advanced Research at Bangalore. With several accomplishments, I would certainly like one of our organizing committee members to introduce the speaker to the audience. So thank you once again. Please join hands in welcoming Professor Waghmare to our campus.
Thank you, sir, for your welcome address. Now I would like to request Dr. Pranab Mandal, Department of Physics, to introduce our distinguished speakers.
Good afternoon, all. So I have the immense pleasure of introducing our today's eminent guest, Professor Umesh V Waghmare. Actually, he has taught me, so it is even my it's my immense pleasure. So Professor Umesh Waghmare received a BTech with Institute Silver Medal Engineering Physics from IIT Bombay in 1990, and a PhD in Applied Physics from Yale University in 1996. He worked as a postdoctoral research associate in physics department at Harvard University before joining Jawaharlal Nehru Center for Advanced Scientific Research in 2000, where he is presently professor in the Theoretical Sciences Unit and a J.C. Bose National Fellow. He is presently distinguished adjunct professor at Temple University and the president of Indian Academy of Sciences. Professor Umesh V Waghmare's research interest entails ab initio modeling and simulations of multifunctional materials, mechanical behavior, nanostructures, topological insulators, and materials for energy and environment. He is an associate editor of Nanoscale and Nanoscale Advances. Professor Waghmare is a recipient of DuPont Young Faculty Grant Award in 2003, MRSI Medal 2004, BM Birla Award for Physics 2005, DAE Outstanding Research Investigator Award 2009, IBM Faculty Award 2009, SS Bhatnagar Prize in Physical Sciences 2010, and the Infosys Prize in Engineering and Computer Science 2015. He was recognized as a distinguished alumnus by IIT Bombay in 2017. He is Fellow of Indian Academy of Sciences, National Academy of Sciences, Allahabad, the Indian National Academy of Sciences Academy, and Indian National Academy of Engineering. It is, I again welcome Professor Waghmare, and I'm sure you were waiting to experience his lecture. I now request Professor Umesh sir to deliver the distinguished lecture.
Yeah. Thank you, Professor Rao. Thank you, Pranav. And I thank Professor Thapa and his colleagues for inviting me for this lecture. It's a pleasure for me to be back at SRM University in less than a year and witness the tremendous growth and developments that are happening on the campus. So let me get started with my lecture today. It's on how materials shape technologies, past, present, and future. This lecture is really meant for general audience, assuming that there are people from colleges and different disciplines of science, engineering, or even arts. So please bear with me if it is too simple for some of the experts in the audience. But there's a lot to learn from the history, how to look at it the way I will show you how things have evolved and how science and engineering efforts have gone into this development in the past and at present. Let me get started with something which all of you have seen it in the newspaper, articles or popular media. You heard of Big Bang theory. It started with a huge bang, which was a very compact object with huge amount of energy, no mass. And this was at a very high temperature. See, the temperatures are in 10 raised to 27 degrees centigrade. We can't even imagine that. Yeah? And in a very small time, fraction of a second, it evolved. It formed electrons, quarks, neutrons, and on x-axis here is the time axis. And as you see, in 1 second, lots of things started happening. Hydrogen nucleus formed, and 15 billion years have passed now as we live today in the galaxy that we belong to. And all along, you will see the temperature has been dropping. Yeah, that's why this process is called condensation. So as temperature dropped, many different types of things formed. This was a natural course of events. And the principle behind it is a very fundamental principle in physics. It's called the spontaneous symmetry breaking. Usually as temperature reduces, symmetry lowers and diversity increases. And as something goes from high energy to low energy, this will be higher temperature object and this will be the lower temperature object. And this is high symmetry object, this is lower symmetry object. Okay, so this is how matter got created and diversified. Yeah? And it continues to happen today. And this spontaneous symmetry breaking in the statistical physics is also known as phase transition. All of you know, for example, melting of water into ice. It's a phase transition. It also involves a similar breaking of symmetry. Yeah? So this continues to happen, and world of materials is very fascinating because those ideas from Big Bang type of evolution, you can test it using simple materials that exist around. So the world of materials today is made up of lots of elements. This is the periodic table. All of you have seen it in high school chemistry text. And these elements are result of essentially spontaneous symmetry breaking starting long ago from the Big Bang. Yeah? And the broken symmetry in the process. And you see, life started about 4.4 billion years ago. And then the humans came about 100,000 years ago, Stone Age about tens of thousands of years back, and so on. So the way we use this diversity in materials for our functions has really determined how they impacted the society that we lived in, that each age is named after the material. Well, let's look at it even more interestingly. On the y-axis is relative importance of materials that were used by us in the course of history, starting from 10,000 BC. And on the x-axis is date. You will see the first thousands of years, most of the materials used by humans are natural materials, right? You have wood, skins, fibers, and you also have stones, flint, and pottery, and so on. Yeah, these are all natural objects. And of course, those are the ones which were available and used as tools by humans in the beginning. Interesting thing you will see is gold is one of the first metals known to us. Are you surprised? It's not abundant on Earth as much as we would like, but it was the first metal known. And the reason for it is, as you know, gold is a noble metal. It doesn't react with anything, and that's why it's easier to find it in the natural form, in its pristine form. Yeah, and that's why that's the first metal known. You will see there was a Bronze Age followed by Iron Age later, but you will see one very spectacular thing, that this is the metal part, and the relative usage of importance of metals kept growing as we reached around 1940s. Until then, metals were the sort of more and more increasingly important set of materials that humans used. And after 1950, something changed. This trend reversed, right? Relative importance of metals started reducing, and you will see these other materials took over. So what happened is a very interesting scientific phenomenon. Quantum physics was developed in 1920s. And that was the trigger for this reversal, as I will go through this talk to explain to you how scientific, basic science development influenced the way we lived and the technologies we used. And so we'll go through that. So let me start with materials from the past and also how they are used today. Of course, the Stone Age is the first one I'll start with. And in this age, one of the major discoveries was fire. You know, to discover fire was very important, was a significant event. However, until we could control fire using some tools, it was not a useful concept or entity to have. And that led to basically ceramics, which could withstand very high temperatures and fire. And this is a picture of a flint axe, which was commonly used by humans as a tool in many things. So that was followed by ceramics. All of us know ceramics today, but they have a very long history. China had developed porcelain, and in the late Stone Age, there were clay pots or pottery, which was made also 5000 BC. It's that longer history. And of course, they are very hard materials, much harder than metals, but they are very delicate, and they can be heat. If you heat a clay to about 1350 degree Kelvin, you can basically make ceramic material. Yeah? Of course, the modern day ceramics are very different. We use extensively ceramics in various technologies, and here are some examples. Smart materials, piezoelectrics. There is a lab in SRM here, which is focusing on this type of oxide ceramics, which are used in a number of applications. You will see in the next slide. Dielectric materials, which are used in capacitors. Phosphors, which are used in light. Magnetic ceramics, which are used in making memories of computers. And refractory materials, you know, in the nuclear reactor where the temperatures go very high up, you end up using refractory oxides. And those are also ceramic materials. And oxides, for example. So glasses are also a class of ceramic materials, very old, long history. But the modern incarnation of glasses are in optical fiber cables, which are used in our communication network, lenses for cameras, and so on. Also in biomedical applications, you have ceramic teeth, which are often used as caps after root canal surgery. So smart material, a ceramic, this is the example of a ceramic. One example is piezoelectrics. These materials are useful because they have an electric dipole moment, which is spontaneously present in these materials. And if you apply a mechanical force to it, you can change this dipole moment and generate an electrical signal, which can be detected in a circuit. Conversely, you can apply electrical voltage to this slab and change this dipole moment and make it expand or contract. So this is called smart functionality because this can be used to sense changes in the mechanical changes in the environment, and this can be used to actuate mechanical responses through this material. So for example, the mobile phones you use have very high quality speakers and high quality microphones as well. Do you know how they work? They use basically this principle. Sound wave is essentially a mechanical stimulus that generates electrical signal, and conversely, you can use electrical signal which can create a sound wave. Yeah. So this is how these are materials are very useful. Next is steel. Of course, Iron Age is again very long history, 4000 BC. And in Africa also, this has been known for more than a couple of thousand years ago. In India, the famous steel is called ceramic wood steel. Yeah, it's on.
Oh, yes, sir.
Thank you. Okay. So, of course, steel has very long history, including the Chinese who knew it for 400, more than 2,500 years. But steel became a very big change in our lives only in 1857. You know, that's where the process was developed. So steel has been known to us for a long time, but this is an example to tell you until you can make certain materials on a large scale, you can't really use them to so as a game changer in technological applications. So it's a very simple principle. You see, this is a vessel made up of refractory lining, something I introduced to you, made up of ceramics, which can withstand very high temperatures. Steel is put in here and it's melted, steel as it comes from the iron mines, and air is pushed through here at the bottom and rushed through it. And the job of this air is basically to oxidize any impurities which are present in the steel. And in the end, you recover a lot of pure steel within a large scale. This process, Bessemer process, was an inexpensive industrial process for mass production of steel. And after that, you see, railways came up. Until then, we could not have steel on the scale that we could afford a railway or a large scale transportation. And all of us know transportation is a big change in society. And that basically introduced so many changes in our history. Japan and Korea are classic examples who are great beneficiaries of their ability to make steel on a large scale, and which helped them in their economic development. Okay, so this is from the past. Of course, this is not a talk which will exhaustively finish all the cases. It's too large a subject. But I think this is a time I will tell you two stories. I think students here in the audience shouldn't get bored. So the first story is something you have seen in a movie called Titanic. And all of you know Titanic was a magnificent ship which was designed by engineers with a great thought, care, and meticulous thinking, design. Unfortunately, they never expected that it would sink because they believed in their design and sort of prediction. But it sank, all of you know. And the reason behind it is rather scientific, at least believed to be so. And it was the fact that many materials, if you cool them down, they become brittle. They become easier to break. And when they designed Titanic, they didn't expect that the temperatures would drop to the levels where some parts of the ship, particularly the hull steel, the welding joints would become brittle. And it's there the failure, mechanical failure occurred, and then the water gushed in and led to failure of Titanic. This is one scenario people believe behind the failure of Titanic. So there's interesting material science called ductile to brittle phase transition as you reduce temperature of a material. Next example also involves the same transition, again a historical example of how Napoleon lost his war in Russia. Yeah, and the science behind it is the Russian soldiers had armor whose buttons were made up of tin. All of you know tin. You have held tin cans in your hand, right? But tin is very interesting. It comes in two crystal forms. At room temperature, it takes beta tin structure, where each atom of tin is surrounded by 6 atoms of tin. It's called coordination number in chemistry. And this is a ductile form of tin. But as you reduce temperature of tin, it suddenly changes its crystal structure, how the atoms are arranged in the crystal, and it becomes this diamond structure, and that has only 4 atoms surrounding each atom of tin. And this is brittle. This is like silicon, chalk, and it breaks. So at the low temperatures in Siberia, basically this led to the break in the armor of Napoleon's army, which is believed to be the cause for one of the important causes for the defeat of Napoleon in Russia. Okay, so after these two stories, let me come back to the materials of 20th century, and these are really eye-opening examples as well. Let me take the first one, which all of you know, Wright brothers. They are credited for development of aeroplanes, which many of you have used, I'm sure. And you know, if they didn't think of a particular material, which is basically an aluminum copper alloy for engine of the plane, they could never fly the aircraft. Why? Because if they use steel, which was of course available at that time, the weight of that airplane would be so high that it would never take off. And the science behind this alloy is very simple to understand. Yeah. So if you take aluminum and copper, their melting temperatures are given here. Aluminum melts at a lower temperature than copper. So if I take a liquid mixture of aluminum and copper and cool it down, right? The first of the two which will freeze is copper, and it forms these little particles in the matrix of aluminum, which will freeze at a lower temperature of 660 degrees centigrade. So what happens? This is a very interesting concept called precipitation hardening. And that leads to formation of a material which is light like aluminum, but it is very tough because the carriers of this mechanical deformation dislocations get stuck at the interface between these two materials. Yeah, and that's what was very important for development of aeroplane by Wright brothers. The next example is of a jet engine, and all of you have taken, probably most of you have taken flights. The last one I took to come to Vijayawada didn't use a jet engine, it was a propeller aircraft. But for long distance flights, most aeroplanes use what are called as jet engine. This is the engine which is below the wings of a big aircraft that you take. Yeah, and it's a very simple, small object actually in comparison with the full aeroplane, but it's a really masterpiece of technologies. Yeah, you will see this is what you see from outside. These are just fans made up of titanium, but the key element, key aspect of this jet engine I want to draw your attention to is these blades, which are the turbine blades, which are made up of super alloys. And the interesting thing is, you could not take a flight from London to New York or Bombay to London if these materials didn't exist. Yeah, why? Because efficiency of a jet engine is dependent on the temperature at which you operate this engine. Higher the temperature, higher is the efficiency. Unfortunately, that means to fly from London to New York, you can only afford certain amount of fuel on the plane because it's too heavy to carry. And you need a high efficiency engine which can use just that much fuel to fly that distance. Yeah, so the temperatures at which this has to be operated is around 15 degrees centigrade at 10,000 RPM. And for that, you need a material which will still be strong and not break down. As I told you, most materials, when you bring them, heat them up, bring them closer to the melting temperature, they start bending, deforming, right? Flowing, you can call. right? Because near melting temperature, the strength comes down. So you need a material here which can operate at this temperature and not deform. And these are super alloys. These are called super alloys because they can be operated even at 80% of the melting temperature that they have. Yeah. So imagine this is how critical it is. If you didn't have super alloy, you just couldn't take intercontinental flights. So these super alloys also involve very interesting material science. Yeah, they contain nickel. This blue region means nickel, and gamma prime here is basically nickel 3 aluminum. And this is an example of a material where atomic scale science, this interface is shown here at atomic scale. These are nickel atoms and this is nickel aluminum atoms. And you will see that the present generation of these alloys contain about 10 different elements which are substituted in this region to make this interface extremely robust and tough. Yeah, and so this is how these materials have developed over 5 decades, and this development really involved engineering at atomic scale. Yeah, and that's sort of is behind this thing. The next set of materials, which all of you have seen again, are polymers. Here is a little history about polymers, started in 19th century. But the most sort of important polymers were developed in 20th century first half. Polyethylene, which basically is known as plastic today. Now it's so much that we don't want any more of polyethylene for the environment. Of course, the Nobel Prize was given to Schrodinger for this work. This is another set of polymers called nylons, polyamides, which are very strong. And the last example here of polymer is Kevlar. Kevlar is made up of aromatic carbon rings making polymers, and these are really tough, strong materials, stronger than steel if you count strength per gram. Yeah, and these are used in tires, armors. They are used in bulletproof jackets as well. Yeah, so polymers is another thing which was developed in this beginning of 20th century. Okay, so it's time for part 2, because that's where I told you quantum physics was developed. And until now, all materials applications I told you revolved around the fact that something is very tough, something is very strong, it won't break, right? But once people knew quantum physics, they knew how electrons also behaved. Until now, we didn't talk about electrons in a material much, other than simple conductors. So this was the birth of solid state physics in 1940s and 50s. Basically, until then, much work on quantum physics was completed and simple ideas were developed. And material science became an interdisciplinary science involving confluence of physics, chemistry, and engineering, mathematics. And basically, the first department of material science was developed in 55 in Northwestern universities. And that started the age of modern materials, and basically exploiting or employing how electrons behave in a material as well. Okay, so material science is really a unique type of science, and that's why I want students to get motivated. This involves all basic sciences as well as engineering. Ideas are very exciting and of course of great remarkable impact on our society and livelihood. So it involves combination of different sciences. And here is a one sentence summary of material science. Some of you who like cooking will ask the same question. If I take this raw material in kitchen and cook it in this manner, what will be the appearance and taste of the food that I cook? Yeah, that's an important question. In materials, that's exactly is the question. How the history of material, starting from its processing, influences its structure and hence properties and performance. It sounds very simple as I defined it, but it really involves a lot of interesting scientific and engineering ideas. So in material science, basically there are 4, it's viewed as a tetrahedron paradigm of material science. It starts with processing. How you process a material is very critical in what comes out and its properties. Because processing determines structure, structure determines properties, properties determines performance, and central to it is how you understand the material, and that's where experiment and theory have to work together. And quantum physics, by the way, as I show here, comes only in one side of this tetrahedron so far. Quantum physics only gives you access to the relationship between structure and properties. By the end of this talk, you will see there's a lot more that we don't understand, and there we have to go beyond quantum physics. And I'll make a case that machine learning is a big game changer today, which allows us to access those ideas and the relationships as well. Yeah, so it's a really exciting science that affects society. So let me now give you how, so as I told you, materials have been evolving, and the science of materials also has been evolving. So how do we think of a material and imagine how it behaves? Yeah. So here are a few examples which are of current relevance. The first example is renewable energy conversion. For instance, you start with a water molecule and you split it to generate hydrogen molecule. Some of you here are working on this problem. And you use a catalyst to do this process along with some energy input as well. Yeah. What does it involve? It involves rearrangement of atoms. You take another application here, it's a solar cell. Solar cell means light is absorbed by this semiconductor and electron gets to higher energy, emitting a hole, and you generate this electron and hole. So electron and plus charge particle hole are rearranged in a crystal as a result of absorption of light energy. Next is energy storage. Whether you have a battery, this is a simpler one to look at, lithium ion battery. All that happens when you use a battery in your laptop or a mobile phone is lithium ions are getting rearranged. They move from cathode to anode, and when you recharge it, they go back to itself, their cathode. Yeah. So this process of storing energy essentially means atoms are moving around. And all of you know from high school physics, if I lift a material object, I do mechanical work, right? If I move atoms like this, of course, it involves work and hence energy. So one very fundamental way of thinking about materials is what is the work done or energy consumed when I bring atoms together to form a given crystal or a material. Yeah. So the fundamental ingredient of a theory of a material or a simulation is how atoms interact with each other. What's the potential energy of a collection of atoms, right? And this energy is of course mediated by electrons. Electrons are the hands which are shared between the neighboring atoms, and it's like a glue which binds atoms together. So the theory will be of basically electrons, and it's called first principles theory. In fact, today morning I saw the computational center here, part of it is focused on this type of ideas. It's called first principles theory, meaning in that a material is viewed as a soup of electrons which are running around in the tight lattice of nuclei. These are nuclei and these are electrons. Electrons are shown as waves because they are much lighter and their motion can be treated only using wave mechanics or quantum mechanics. Whereas nuclei are much heavier, their motion can be treated using Newton's laws of motion. So within this picture, what we do, or one way to think about a material is, for any given snapshot of nuclear positions, electrons are so rapid and agile, they instantaneously rearrange themselves to minimize energy. And that's what gives rise to the interaction between atoms. Yeah, and as a result, what you get is the total energy of electrons or nuclei, which chemists like to call as interatomic potential, or how atoms talk to each other. Okay, so this first principle theoretical approach basically has a very simple conceptual ingredient. You look at total energy, and this has two parts. One is the quantum mechanical ground state energy of electron, the minimum energy of electrons, and the classical electrostatic repulsion energy. And this is the only equation in my talk, and it's as simple as it can be. In fact, getting this first quantity is very challenging, and for that you need quantum physics. And even if you know quantum physics, you can't really do it realistically for any system unless you make approximations and use a computer. And that's where the computing facility partly is used for in SRM University as well. And for this work, we use what is called as density functional theory. Walter Kohn received a Nobel Prize in chemistry for this development. Okay, so just like in high energy physics, you have heard of what is called a standard model of quarks. And elementary particles in nature. This is called the standard model of materials. Basically, the total energy function, which I defined, is the model for interatomic interactions. And from that, you can derive many properties of a material. And that's the power of this simple approach. Okay. If you minimize the total energy, you can get structure. And I'll show you, you can get 3 types of structures from this analysis. And the properties of a material are related to differences in this total energy or derivatives of total energy. Yeah. So sorry, this was a little small technical section in my talk, but it's necessary for you to know what is the present scientific language to think of a material, or a chemistry of a material, or physics of a material, using these quantum physics ideas. Okay, so if I minimize the energy, I can predict this structure of a material. Here are basically atoms. How atoms are organized in space is basically the structure of a material. You can also get it experimentally. For that, you will need X-ray diffraction, but in theory, it's a very simple sort of simulation which gives you this. Second is called dynamical structure, means all of you know that even if I have a crystal, atoms are not sitting in one position. They are all thermally vibrating around their mean position. And that's called dynamical structure. No atoms are stationary in any system. And how they are displacing around is basically given by this. It's the frequency of vibration on y-axis as a function of inverse wavelength. It tells you how stiff are the bonds in a material if you think of it as a spring constant. Okay, so some of you here do Raman spectroscopy. Raman spectroscopy essentially listens to the vibrations of a molecule or a crystal. And those are essentially these frequencies that you see here. And Raman is like a fingerprint, meaning if you heard me for half an hour, if I step outside this hall and I speak loudly, you can immediately guess that it's Umesh, just listening to my voice. Yeah, so voice is a fingerprint. For a material, vibration is a fingerprint. And Raman essentially measures the frequency of vibration of a material or a molecule and can be used to identify what molecule or material it is. And the last one is electronic structure, and I'm sure the electrical engineers here would have seen it. If you have energy of electron waves and inverse wavelength, you get basically valence band of electronic states, which looks like this from the simulation, separating conduction band, which are not occupied by electrons. And this band gap basically tells you the material is either a insulator or a semiconductor. If there's no gap, you get a metal, because these become the highway of electrons. In a metal, they can carry electricity very rapidly. Okay, just to end this small technical section, particularly for students, if you want to simulate a material using these ideas, you don't have to go to a lab at all. You know, this is the advanced development in this theoretical work, is you can just download these software packages which have been developed by physicists and chemists and simulate fairly interesting material on moderate computing resources. Yeah, so science of materials has become accessible to very moderate resources if you restrict to simulation type of work these days. Okay, so let me come back to the modern materials. See, now we know the quantum physics, and then people started thinking about electrons and how electronics can be influencing technologies. So here is an example of a transistor. A transistor was developed by these 3 individuals, Shockley, Bardeen, and Brattain. And again, this is a very inspiring story, particularly for students. William Shockley was a PhD in quantum physics from MIT. And he developed a theoretical concept of a transistor in 1937. Yeah, knowing quantum physics, he imagined this idea. And using, these are engineers, no, Bardeen and Brattain. In fact, Bardeen was a engineer by a bachelor's degree, but he was a PhD in mathematics and physics. And Brattain was an engineer at Bell Labs. They developed this point contact germanium transistor. The idea is very simple. If you are looking at electrical current, which is passing through this NPN semiconductor junction, this is the 3rd electrode, which is like a tap, which controls the flow of electrons through these channels. Yeah? And this transistor, of course, revolutionized the way we lived. Yeah, everything you have devices, electronic devices, gadgets, of course have transistors in it. Bardeen, who was an engineer, was the only person to get 2 Nobel Prizes in physics. One was for the transistor and another one was for superconductivity, which we'll come to very soon. So knowing materials, knowing quantum physics is again not enough. All of you know silicon is very special. And why? The reason for it is here. That ability to grow ultra pure silicon was key to the semiconductor revolution. Yeah, silicon is known to us for centuries. It's not like it was known only in 1950s. But the ability for us to grow it, and here is how silicon, pure silicon is grown. Basically, this is like an ironing box, which has a high temperature here, and it's very gradually moving to the right, moving heater, and behind it, it leaves very pure crystalline, like a cloth whose wrinkles can be ironed out behind it. So defects are lost, and basically this is defective solid silicon, and it becomes pure and pure as this moving heater moves to the right. And indeed, to do this, of course, many metallurgy lessons were important in mastering this process. Okay, so how can we use these semiconductors to generate light? Because you will see that this is bringing us to a new revolution in technology, light revolution. If you want to create light from a semiconductor or an insulator, the process to accomplish that is like this, that you excite an electron to the conduction band of a semiconductor, and when that electron comes down and mixes with this hole, it generates a light. And this band gap, the energy separation between unoccupied states and occupied electronic states, gives you the color of the light that it can emit. Yeah, very simple. It's like an excitation. Only certain wavelengths are emitted by a given material. Silicon and gallium arsenide unfortunately cannot emit visible light because the band gap of these compounds is less than EV, or about an EV. Yeah, so they can't really be used. 1 EV will be in the infrared region this side. This is the visible range, which corresponds to about 2 to 4 EV. And that is why you will need a semiconductor which has a larger band gap. And that brings us to next interesting idea of light emitting diodes. All of you have heard of LEDs, right? LEDs are everywhere today. And these light emitting diodes again involve the same concept that I told you on the last slide. You have P-type semiconductor. This is conduction band, valence band, and N-type semiconductor. And if you can push these empty electronic states to the right and these excited electrons to the left, they recombine here and emit light. This is called light emitting diode, PN junction. Yeah. And you will see this is a Nobel Prize winning PN junction made up of gallium nitride. Yeah. So this is P layer of gallium nitride, N layer of gallium nitride, and this is an active layer. If you bias it with a positive voltage on the P and negative on the N, they recombine with each other and generate blue color light. And this was a revolution again, because if you finally want white light in your room, you need the entire spectrum of visible light from blue to red. And this was the missing piece, and gallium nitride was the game changer here. Some of you will wonder, gallium and nitrogen, I showed it in the periodic table. All of us have known it for centuries. But the Nobel Prize, you see, work was done in 1990s, and the Nobel Prize was given in 2014. And the reason for it is, even if gallium nitride has been known for decades or even half a century, ability to grow it in a pure form. You see what they did, the main achievement of this trio was to grow it such that only the bottom part of this film is defective and this top part of the film is very pure, high pure, or very low defect density. And if you can grow this gallium nitride with this purity or low defect density, then you can make light emitting diodes out of it. Yeah. So this is the game changer. How it changed our lives, you will see. This is where we started, the oil lamp. And what I'm showing you here is the efficiency, 0.1 lumens per watt. As you went along, there was an Edison's light bulb, which was much more efficient than oil lamp. But you see, this is 3,000 times more efficient than oil lamp, the light emitting diode. So not only we developed a technology to generate light from very simple semiconductor, of course, highly pure, but it revolutionized the efficiency of generation of light. And now you see LEDs everywhere, from televisions to traffic lights, lamps at home. And the reason government is encouraging is because they save a lot of electricity for us. Yeah, and energy is a big crisis. The last example I wish to cover before in the set of modern materials are called superconductors. All of you have heard of superconductors, right? Or no? Yeah, most of you have, I'm sure. So you would think that superconductors are those metals probably which can carry current without any resistance. That's why they are called superconductors. There's no resistance to flow of electric current in them. And that's why they are very good, because you can carry electricity without losing any heat. And if you see the history of conductors, started long ago in 1911. This was Kamerlingh Onnes, who developed a superconductor based on mercury. It was a serendipitous discovery because he was looking at cooling down materials and measuring their electrical resistivity. And he found that in mercury it dropped to 0. And after that, of course, there was, you see the difference. Within 2 years, he received a Nobel Prize, because that observation alone was so striking that you can carry electrical current with 0 resistance. But there was a lot more science in it, and that was uncovered in much later. So one of the very interesting property of a superconductor, for example, lead is a reasonably good superconductor. Niobium is a good superconductor with tens of kelvins of temperature. Above Tc, they behave like a normal metal. You see, if you apply magnetic field will just pass through them. But if you lower the temperature of this material below certain Tc, they become superconductor. Means not only they have 0 resistance, but magnetic field cannot penetrate that material. The very unique property. It's called Meissner effect or perfect diamagnetism. 0 magnetic field. Just like a metal, all of you know from high school physics, if you apply electric field, the electric field cannot penetrate a body of a metal, right? Field inside a metal body is 0. Here, the magnetic field is 0, and that's why it's called perfect diamagnetism. And it gives a very important property to a superconductor called magnetic levitation, meaning if I have a superconductor here and I put a magnet on top of it, it floats on the superconductor. It levitates. Yeah, it's a very interesting property, and this is something, by the way, you can, if I had enough equipment, we could show it on, demonstrate here on the stage. There are some superconductors which can be superconducting at liquid nitrogen temperatures, and this can be shown. YbCO is an example of it, yttrium, barium, copper oxide, and it's a ceramic for which Bednoes and Muller got a Nobel Prize in '87. Yeah. So superconductors, of course, continue to surprise us. Comes with a lot of things, but here is an example of maglev train. This is a real existing train operating in Japan, also some of China and other countries. Basically, here they use superconductivity to lift the train, which is relative to the tracks. There are no moving parts. There are no wheels to this train. Yeah, all it is using is this property that if you have a superconductor and a magnet, it will lift it up. And if you have a strong enough magnet and a strong enough superconductor, it lifts this train up by about 10 centimeters or a few inches. Yeah, and then there's another electromagnetic field which can push this train along the track. So with no wheels, these trains can operate at 500 kilometers per hour speeds. And they're, of course, interesting from this angle. Energy efficiency is a different angle, but I won't get into that at the moment. Yeah. So very remarkable property, very high speed train as well as low speed trains are possible using superconductors because friction is 0. There's 0 friction. There are no moving parts altogether. There are many technologies which are based on superconductors, which we do see in day-to-day life as well. And the first one is something you see in hospitals, in MRI machines. magnetic resonance imaging in hospitals, which are used to scan brains or other organs, basically require very high magnetic fields to be generated. And that's possible to do only using superconductors, because superconductors carry very high electric current and they give rise to very large magnetic fields, which can be used in this equipment. The second example, of course, is power transmission, although we don't really use them. They will give you no loss, no electrical losses or heat losses while carrying electric current. The third example is the SIS junction, superconductor insulator superconductor junction. It's called Josephson junction. And that's a very interesting device which can sense it's called SQUID device. It can sense extremely small magnetic fields. Now, again, I wish to share with you very interesting story and application about it. They sense such small, tiny magnetic fields that in Japan, there were experiments to measure magnetic field just outside the head of a human and try to guess the emotions of a person. Okay, they correlated measurement of magnetic fields with anger or sorrow or other types of emotions of a human. And it's not surprising, because finally your brain is acting on electrical signals. All of you may know neurons, synapses, and charges flow through your neurons when you think or when you express something. And when charges flow, they generate magnetic fields. And of course, these are very tiny magnetic fields because those charges move at a very slow rate. And those fields can be detected using this type of devices. Yeah, amazing technology. Okay, so I think that concludes sort of the materials which have been known for the last century. And that brings me to more modern materials. This saga doesn't end. The first one in this category I wish to share with you is called conducting polymers. There is a lab in SRM University which works on this, called Organic Electronics Lab, where, well, polyacetylene is a classic example, where you see you have pi bond in alternating CC chain bonds. And these three, Heger et al. Got a Nobel Prize in chemistry for this in 2000. And the idea is very simple. Normally you think that polymer or plastic will not carry electric current because they are made up of carbon-based materials. But in this case, along a chain, these pi electrons are highly easy to delocalize. They carry the electric current. Okay, and the OLEDs, organic light emitting diodes, solar cells, many devices are now being made of polymers which are called as conducting polymers or conjugated polymers. The second class of materials are nanomaterials. All of you read about nanotechnology in newspapers or other popular media. And one of the elements, which is the simplest one we know, is carbon. Which is very remarkable in nanotechnologies and nano world. It takes different forms. Carbon is the only element which has this very special property. It can be rolled into a carbon nanotube, which is a 1D object. It can be a buckyball, football-shaped molecule of carbon, which is Buckminster-Fullerene, again a Nobel Prize in '96. It can have, of course, graphite form, which is present in the pencils that you use. And more recently, you can just peel out one sheet of carbon atoms and make what is called as graphene. It's a two-dimensional atomic membrane of carbon atoms arranged in a honeycomb lattice. And this is very remarkable as well. Again, this is a field by itself. It's a full talk can be given on this. I'm just going to tell you what is exciting about graphene. So graphene is this simple honeycomb arrangement of carbon atoms. Each circle here denotes a carbon atom arranged in this beautiful lattice. Again, you see work was done in 2004 and Nobel Prize was given within 6 years. A very remarkable material developed. You will wonder what is so remarkable about carbon membrane. We of course know carbon graphite everywhere. Well, the interesting thing is as follows. Electrons in graphene behave very differently for the structure and chemistry that it has. So electronic energy of in graphene as a function of momentum along x and y direction behaves like a conical structure. If you look at any common material, energy of a particle is given by p squared by 2m. This is our standard classical physics, mechanics from high school. Kinetic energy is half mv squared or p squared by 2m, where p is the momentum, which is a parabolic form like this. But in graphene, actually it is linear. You see, cone means it's a linear energy dependence on momentum. So energy is proportional to momentum, not quadratically dependent on momentum. And more interestingly, if you think of it in a relativistic sense, this is the expression of energy of a free particle in a relativistic mechanics. And if you set mass to 0, you basically get this expression, E is proportional to P. So electrons in graphene behave as if they are relativistic particles. Normally in physics, you may have heard, you can access relativistic physics only when body moves at a speed which is comparable to light. But in graphene, you can access it even in a tabletop experiment without moving much, because the effective dynamics of electrons is like a quantum mechanical relativistic physics, and it gives very high mobility and very unusual, interesting effects in graphene. And that really, in the last 2 decades, have changed, impacted the fundamental research in this field remarkably. Applications of graphene are still coming in, but this is still sort of a futuristic material. In few things, they are still already there in the applications, but a lot more are expected in the years to come. I will end this by basically highlighting some of the challenges that we face and what type of materials are needed for addressing those challenges. And again, this is not a comprehensive list, it's a very short list, and particularly energy and environment. All of you know that India has declared that by 2070, we want to be carbon neutral. You know what is carbon neutral? Means you don't add any more greenhouse gas like carbon dioxide or methane to the atmosphere. And it's not easy. If you are asked to change your cars to electrical battery-based cars overnight, it's not easy. If you are asked to use cooking gas, remove cooking gas and replace it with electrical stove, it's not going to happen easily, because first, you don't have so much electricity available, and second is it will take a sort of long time to change all the infrastructure for that. So clean energy is one very big challenge for us. India's target is to 2070, but other countries want to achieve it by 2050 even. Yeah. So of course, one problem is you use too much of fossil fuel, which generate greenhouse gases, global warming, and which also leads to climate change, adverse climate change. So there are 2 solutions. One is, of course, to use renewable energy like solar panels, wind energy. And also, second is to use hydrogen, which is a clean fuel. Hydrogen, if you burn, you will get water. And if you split water back, you will recover hydrogen. So it's a completely recyclable fuel which does not emit greenhouse gases. So I know that many groups in SRM University are engaged in these research activities, and it's really heartening to see that. So many of you are looking at solar panels, some of you are looking at reduction of CO2 to useful fuels, some of you are looking at production of hydrogen by splitting water and so on. So here is a sort of slice of this technological challenge. So you start with solar energy. You can use solar energy in 2 ways. One is you can use solar cell, electrical cell, which all of you have seen these panels, and generate electricity. And of course, solar energy is available only in the daytime, right? You can't generate this electricity at night. So you need to store it. You can store it in sodium batteries or lithium batteries, which are too expensive, or you can use that electricity to split water electrolytically and generate hydrogen as a fuel. So hydrogen, in some sense, is a storage of energy, chemical storage of energy, which you derive from solar energy. Or you can also use solar energy to photocatalytically split water into generation of hydrogen. Yeah? So the upper proportion of this figure basically tells you flow of energy, energy conversion, and also storage into hydrogen. Whenever you need electricity back, you can use hydrogen in a fuel cell and generate electricity. Yeah. So this is indeed, and I know that there are many labs here in SRM which are looking at various of these processes, and each of them require you to have a material which will do that job. Either you need an absorber which can absorb solar energy and convert to electricity, or you need a catalyst which can burn hydrogen to generate electricity, or you need a catalyst to split water. And in sodium batteries, of course, you need materials which are cost effective and can be used to store the sodium ions. The second lower part of this, by the way, is a different type of technologies. One is, these are the environment related technologies. If you burn fossil fuel, you generate a lot of these gases and you want to use catalysts to basically convert them to something less harmful. And second is any device you have, whether it's computer or it is automobile or anything else, 40% of energy is wasted in generation of heat. And that's a large part of energy. And this wasted heat can be converted to electricity using thermoelectric material. In fact, this is a time to tell you that technological challenges in very different domains often are similar. At present, if you look at computers, I saw one lab today in SRM University is looking at fluid-based cooling of the CPU chips in a computer, right? Not using air, but to use fluids. And if you ask aerospace industry, the same challenge exists today. In modern aircrafts, so much energy is generated. And you know, when the plane is flying 10 kilometers height, it cannot lose that heat to air. There is not enough air at that altitude. So where will it dump all the heat? So how do we manage heat in aircraft? Has similar challenges as you face the challenges. How do we manage heat in a computer? That you have faster and faster circuits, we generate more and more heat. How do we manage it? Yeah. So I'm going to just give you one example of it, how heat, this is called thermoelectric technology, and why it is very exciting science. Okay. So this is how waste heat can be utilized or managed in some sense. It's a thermoelectric material. If you use this material to be sandwiched between hot side and a cold sink, the positive charges will move this way and negative charges move this way by if you have N and P type of thermoelectric material, and that generates an electric current. Okay, so when you have temperature gradient available from hot side to cold side, you can convert that temperature gradient to electricity. And that's called thermoelectric conversion of heat into electricity. Yeah, and it's a figure of merit is given here called ZT. This is Seebeck coefficient squared. Seebeck coefficient tells you how efficiently you generate electric current. Sigma is the electrical conductivity. It should be very good conductor of electricity so that you can generate a lot of electrical energy. But thermal conductivity should be very low, because if thermal conductivity is high, all the heat will go from hot side to the cold side. Yeah. So you need a material which is very fascinating. It should have high Seebeck coefficient, and it should, high Seebeck coefficient is seen in a semiconductor. You need a high electrical conductivity, then you need a metal, and you need a very low thermal conductivity, then you need a glass. So same material should behave like a metal, semiconductor, and also a glass. And that's a scientific challenge. How can we cook up a material which will have a combination of these three properties? And that's why the design of a good thermoelectric material is a big challenge today. Yeah? And by the way, thermoelectric can be used to generate electricity, or you can also use it to refrigerate. It's a precision refrigeration where you can apply electric current here and generate exactly the low temperature that you want with no moving part in the fridge. Yeah? So it's a very attractive technology. So this challenge is, of course, occupying lots of people in research today, and I won't go into details, but it involves rich fundamental science and huge activities devoted to that. The last one I will show you is, I know that this is not a research talk, but I can't resist showing you some very exciting discovery from my own research in the recent years. And this is basically the hafnium oxide. It's a crystal made up of hafnium and oxygen atoms. And what we showed in this work is very fascinating. Yeah. So hafnium oxide, as you see, has oxygen atom and hafnium atoms. And you can switch one plane of oxygen atoms to up or down direction at the way you want. And it still is a very stable crystal. So it's a crystal which allows us to control its local structure at atomic scale using external electric field. And if you take another competing material called lead titanate, which is also a very fascinating technological material, it doesn't have this property because if I try to switch only one unit cell of a crystal, it leads to entire crystal switching to the opposite direction. So this hafnium oxide that we have predicted allows you to store binary information in sub-nanometer scale, half a nanometer scale. Yeah. So with this, you can develop computer memories, which are amazing because you don't need to nano pattern hafnium oxide. You want smaller and smaller memory devices. In hafnium oxide, you can have a single crystal with no nano patterning necessary, but you can deposit electrodes on the nanometer scale and are able to switch electric dipoles inside it. Yeah. So this is sort of is a material which we believe is a futuristic material which will give rise to ultimately high memory density devices. Lastly, I will sort of summarize that machine learning is a big development today in this field. Just like quantum physics was a big thing in 1920s or 50s, machine learning today is able to combine synthesis of a material composition and any parameter you have, even experiments for that matter, and develop predict properties using learning from this data. And very important in this exercise is combining experimental and theoretical data so that your predictions are very easy to translate into real lab applications. So when you will see that when you develop a material, it takes at least 20 years from discovering it in the lab and then using it in a real world application, deploying it in the technology. But if you use machine learning, you can speed it up significantly by having an integrated approach, which not only looks at the performance based on structure and composition, but it starts from synthesis or processing itself. Yeah, so machine learning is one big thing, and I understand that groups at SRM are also investing in the domain of machine learning in material science. I'll summarize in the end. I hope I have given you a flavor without going into too many details that materials are key to technological revolutions. Secondly, they involve very exciting and interesting fundamental science. And thirdly, it's a very interdisciplinary field, and it has the promise to tackle future technological challenges, which often require engineers and scientists to work together. And they're going to be key to solving our challenges in energy, environment, health, and water. I acknowledge in my research, I worked with my students and a few groups. And thank you for your attention.
Thank you very much, sir, for your enlightened talk. Now we all are excited to know the impact of materials, starting from these natural materials to today's smart materials. Now I would like to request our registrar sir to present the memento to our distinguished speaker. Now, I would like to request Dr. P. Rajapandian to give the concluding remarks.
So good afternoon, everyone. On behalf of the organizing committee, first and foremost, we would like to express our heartfelt gratitude for our distinguished guest, Professor Waghmare, for his invaluable insights. We are truly fortunate to have had the opportunity to listen to you, and we are grateful for the enlightening lecture. So it is evident that materials play an indispensable role in shaping the course of technology. Let us foster to contribute the spirit and innovation as we delve deeper into the boundless world of materials and technology. We would like to thank our President, Chancellor, and our advisor, Professor V.S. Rao sir, and our registrar for their continuous support and encouragement. Our sincere appreciation goes to the ITKM department, communication department, CLM, and everyone who helped us behind the scenes to ensure the smooth execution of this event. We would like to thank all the attendees for joining us today. As we conclude this event, we hope the insights gained today will continue to inspire us and drive us forward in our respective fields. We look forward to have more such enlightening gatherings in the future. Once again, thank you for being a part in this event. Have a nice evening.